All right, so here we are with differential equations and the slope fields. So we're going to introduce the concept of a slope field to this example. Consider we have this first order differential equation, dy dx is 0.2y. Now, a function of f is a solution of this equation if y equals f of x satisfies equation 2 for all values of x in the domain of f. Now, geometrically interpreted, what we can do is we can get the slope of the solution curve that passes through whatever point x, y it is. So, for example, if y equals f of x is a solution of equation 2 that passes through point 0, 2, then the slope of f at 0, 2 is given by, well, now we plug it in and we get 0.4. Okay, so we indicate this relationship by drawing a short segment of that tangent line at the point 0, 2. So at 0, 2, we have that slope. Okay, then we do it for negative 3, 1. Plug in that, figure out what the slope is. And then we say, okay, well, that's now at this. Then we do it also for 2, 3, and we figure out what the slope is, and we sketch it in. And so we sketch it in for all those. Then what we do is then we say, okay, well, a possible graph is if we combine all those, we get something like that. And so that's how we can use these slope graphs to do it. And so we actually have to come up with a lot of different points, along that line to figure out what it actually looks like. So that's why I say it's one of those things that it's more computer oriented, or it's already there drawn for us. We're not going to calculate those for every single graph. Now, if we continue the process of drawing tangent line segments at each point grid in that figure 1, a task easily handled by computers, like I said, but not by hand, we obtain this slope field we see in figure 2. Now, in general, this slope field for first order differential equation is obtained by drawing tangent lines, the segments of them at each grid point on whatever size of graph you make. So in this one, it's a 5 by 5, and it's 5 each direction. Okay, so you figure out what the slope is at each of those, and then from there we can draw different curves. Now, what we can now show is that y equals c times e to the point 2x is a solution of the equation 2. Remember, equation 2 is this point 2 times y. Oops, where are we at? For any real number c. Now, if we substitute y equals c e to the point 2x into equation 2 to see if the left side is equal to the right side for all real x, we get the following. So we're going to plug that in and say, okay, well, dy dx is going to be what? Well, that's going to be d dx of this thing, which gives us 0.2 times c e to the point 2x. And our right side is going to be 0.2y. Well, 0.2y is, we're going to take the derivative of that. Well, that's equal to that. And so equation 3 is the solution because both sides are equal. So this is equal to this. Now, which values of c will produce solution curves that pass through the point 0, 2 and 0, negative 2 respectively? Well, if we substitute those coordinates into each of the points into equation 3 and solve for c, we get the following. Y equals 2 e to the point 2x and y equals negative 2 e to the point 2x. Okay, so we get, two pieces for equation 4. Now, the graph of equation 4 is going to be shown here on the next slide. It confirms that the results shown in figure 1b, which was before, that there's a general solution to the differential equation of 2, and the functions are actually specific ones. So the specific ones are that one and that one. Now, if you keep drawing all these in for all the different points and come up with different ones that goes through maybe this point, then you'll have something different. If it goes to that point, you're going to get a different graph. But for the point we told it to go through, we get those two lines as far as what our graph is going to look like. Okay, so again, that's a lot of this is for equations done by a computer. They'll come up with a slope graph like this, and then you have to do something like this. You have to plug in left and right side for specific points, and then you come up with, okay, well, it's this one and it's this one is the only one that actually works. All right, so let's stop there and we'll come back for some more.